All right. So good afternoon, everyone. So to get started, any questions about assignment 2? No questions? So who has already tried? It's very easy, no questions at all?
I'm pretty sure the way I've done it is wrong because I get a really stupidly big number. So
The number is so big that you cannot write it, actually.
my calculator basically died when I put it in.
That's a good sign.
Oh, okay.
So apart from that question, any other question? All right, so that probably means you need a harder assignment, right? So I will try to work on that. Okay, so let's get started with today's lecture. So that's going to be the second lecture about modeling. And again, it's the same idea. We're gonna do some puzzles together. Then I'm gonna present some puzzles for you to do, and we will go with the lecture like this. And the lesson to be learned again is about solid calculations. You have to model your problem. You have to find the variables, the constraints, and the objective. And then if you're minimizing or maximizing, then the objective is very important. Sometimes the problem is just to find a solution. So that means, you can pick any point from the solution space. You have to be very sure about, very sure about what you're trying to maximizing or minimizing. If the question is not clear about this, you have to make assumptions of what I mean by maximizing and minimizing. So these are all very important questions. Variable, constraints, objectives, what you're trying to maximize, what you're trying to minimize, and if it's just a constraint problem or actually a maximization, minimization problem. So let's get started with this question. Sorry, there may be some interruption. All right, so let's get started with this question. I had to skip this question a couple of lectures ago, but I think that's an important question for you to understand the importance of modeling. So it goes like this. So we have two identical boxes. Their widths, lengths, and heights are the same. And they are cubical, which means that they have the same width, heights, and lengths. One box contains 27 identical iron spheres arranged in rows of 3 by 3 by 3. The other one, the outside spheres touch the walls of the box, and the spheres touch each other, right? So they just keep touching each other until they touch the walls. And the second box, there are 64 identical iron spheres arranged in the same manner, so 4 by 4 by 4. So the picture that you should have in mind is something like this. So if you look at this box from front, you would see like this 3 by 3, and then you have to also imagine there's like 3 rows of this, right? In the box 1 and the box 2, you're going to have 4 rows of this. So you're going to have 3 by 3 by 3, 4 by 4 by 4 of iron spheres. Assuming that the spheres, larger in the first box, smaller in the second box, are made from the same type of iron, which box is heavier? And there's the sphere volume here, formula for that, which you probably need. Okay, so let's try to do this question together. Okay, so the volume of a sphere is this, right? Okay, so box 1, you're going to have, so there's no overlap, right? So there's going to be 3 by 3 by 3, and box 2 is going to be 4 by 4 by 4. Sorry, don't get deceived by my drawing. No, they actually touch each other and they touch the wall. There's no overlapping like I draw here. All right, so how do I solve this question? So the question is, which box is heavier? And and I have this statement here that says, assume that spheres are made from the same type of iron. That assumption is important for this question, otherwise it would become trickier to solve. So what do you suggest me to do? How do I calculate that? The diameter of the sphere or the radius, right? Okay, so let's say this length here is 1, and same story here. The length here is 1. So then, what is the radius of sphere in box 1? So R1, let's say, is going to be 1 divided by 6, and for box 2. 1 divided by 8, right? Now, how do I compute which one is heavier? Yes?
So you should take weight as density times by volume and assume they have the same density.
Cool, yeah. So then I just need to compute the volume, right? All right, so let's take volume from box 1. That's going to be 4/3 pi R1 squared, R1 cubed. And volume 2, 4/3 pi 1 of 8 cubed. So this is the volume of a sphere in box 1, volume of a sphere in box 2. Right, so then what?
Get the ratio of the volumes.
So the ratio of the volumes, like this. So what is that going to give me? Okay, so let's try to do this. So it's going to be 1/6 cubed, 4/3 pi 1/8 cubed. So cut. So that's going to be 8 cubed, 6 cubed. Okay. So now what? How do I compute which box is heavier?
Multiplied by the number of cube of spheres.
Okay, so now let's do this slightly different. So how many spheres I have in box 1?
27.
Yeah, so 3 cubed volume 1. So that's the number of spheres in volume 1. Sorry, box 1. This guy. And the other one is going to be 4 cubed times V2. Again, number of spheres in box 2. So I already have this ratio. So that means this is going to be 3 cubed, 4 cubed times 8 cubed, 6 cubed. Okay, so what does it tell me?
It's greater than 1, V1 is heavier.
Yeah. So can you help me computing this? So let's rearrange these guys, right? So let's put like 8 cubed, 4 cubed times 3 cubed, 6 cubed. Come on, help me out. What is this? You don't need a calculator for this. This is going to be 1, right? So this is going to be 2 times 1/2. Okay, so then the answer here is just 1, which means they will be exactly the same. But you have to make this assumption that the density is the same, so you can compute weight, just using the volume. And of course, this is counterintuitive, right? Because if you look at this, so what does your intuition say? Which one would be heavier from your intuition, box 1 or box 2? So who thinks box 1 from intuition, before you actually solve this question? Yes, so box 2. Yeah, so that's usually the case, right? But, I mean, you know, the spheres get smaller, but the space between the spheres will also get smaller. There's lots of questions like this in geometry, which are very counterintuitive. It's like, you know, you take a volume of, you take a sphere and a box, and then you increase the number of dimensions, and you see how the ratio between, you know, the volumes of these two, you know, these two objects will go with the higher number of dimensions. You know, things like this happen all the time in geometry, which is interesting. Okay, so this is question 1, just to warm up. So let's go to question 2. Again, you know, this is a very common problem in electronics, in engineering. You have here a, you know, just a diagram or, you know, schematic of a PCB, which is a printed circuit board. And you have to connect here points 1 to 1 prime, 2 to 2 prime, 3 to 3 prime, and 4 to 4 prime with a continuous line. So there cannot be any break, cannot cross lines or anything. So I'll give you 2 or 3 minutes to try to solve this question. And of course, you know, there is a very deceiving point here that if you don't pay attention, you'll not be able to solve this question. But the question is, can you solve it? If so, how? If you cannot solve it, tell me why.
Is it possible to go out of the drawing?
No.
Are we allowed to assume you can connect any one point of, like any point of, say, for instance, 2 to any other point of 2 prime? Or is it just center to center?
I don't understand the question.
So, are we allowed to, for instance, connect the bottom left-hand corner of 2 to the top left-hand corner of 2 prime? Like, can we draw that, like, as in what?
Like from outside? Or?
So, look, so if that's the boxes, can the line go from one corner to the other, or does it have to go from...
No, it has to be from inside, yeah. So like from the border?
Yeah, no, as in it is from, like, as in it's the, where the, so 2, so for instance, the box 2 is on a square there. Can you connect from that point on their border to that point on 2 prime?
Can you draw it? I'm not sure I understand.
He basically had it right. So if you got,
Got a box.
for instance, if that's 2, we've got another box that's 2 prime.
Yeah.
Can you connect from that corner to that corner?
Well, I'm not sure where you want to go with this, but it cannot be very close to the border, right? So I mean, this is still, you know, a circuit board.
I'd say we probably
I mean, putting things close to the border may be dangerous.
Okay.
well, in that case, you can't.
So in that case, you really can't do what I was trying to say.
Yes. That's right. Yeah.
You can curve the lines.
What did you do? Oh no, yeah, that's right. That's cool. Yeah.
You can curve the lines.
Oh, sorry.
Because it's a PCB, can you use both sides of the board?
No,
You can't?
it's an old PCB.
Is it strictly two-dimensionally, or
Yes,
can we go
yes,
again?
2 dimension, yes.
I feel like an idiot.
Yep. Okay, so I mean, if you're trying to solve this problem, usually, I mean, that's very normal, right? You know, with your intuition, you have to connect 1 to 1 prime, and 2 to 2 prime, 3 to 3 prime, and so on, which means that you try to do that in order, which means that you will go and do like this, right? So that's your first thing that you try to do. And of course, once you do that, you isolated 3 and 4 prime in this case. So there's no way you can, cross these guys and try to connect them. So there's actually a way to do it. But the easiest way to kind of thinking about this problem is if you kind of relabel these guys. So imagine now that 1 becomes 4, 2 becomes 3, 3 becomes 1, and 4 becomes 2. So, I mean, let's put like this here. So, sorry, 1 becomes 4, 2 becomes 3, 3 becomes 1, and 4 becomes 2. And now, let's connect 1 to 1 prime, which before was 3 to 3 prime, and that's this. And then 4 to 4 prime, which now is 2 to 2 prime, which is this. Right. So looking at this, now there is a clear path between 1 and 1 prime, which before was 4 and 4 prime, and then 3 to 3 prime. So let's try to connect 3 to 3 prime, and then it's going to have this very convoluted way of connecting these guys. And 1 to 1 prime is the same story, so try to go like this, don't connect anything, and then go there. I mean, as silly as it sounds, a lot of the optimization problems that we saw last class, and then we're going to see some more today, they have to deal with these problems, okay? They have to somehow connect millions of components with, respective components. And they also try to minimize the amount of copper that they will use to connect these things, which is a very, very big optimization problem. It's nothing like we solved last week. But again, it's the same kind of problem. You're going to have to minimize the amount of copper used. You want to minimize the area, and you want to maybe minimize the energy consumption. You're going to have all these terms that you want to minimize. And in the end, you want to maximize your profit. So then you're going to have to do all these things. So imagine this is going to be a very complicated problem, but it's the same type of problem that we already solved. Okay, so let's move on. Again, when you see a problem, try to think about the model and then get to the solution. And when you think about the model, always try to identify the variables, the constraints, and the objective. Objective, again, can be minimized or maximized, or it can just be a problem where you try to find points within a solution space. So whenever you think about this type of problems, let me go back here. So you can imagine like a solution space. So, you can imagine your variables. So these are the things that belong to the question. You identify them as variables. And then you can identify the constraints of the question. Maybe there's a constraint here. There's another constraint there. There's another constraint here. And this little region here is going to be called your solution space. So, these constraints are like this. So, I want only points on this side, only points on that side of the line, and only points on this side of the line. So I have 3 constraints, which means like all the points here can be a solution for your problem. But then, if you want to minimize or maximize a function, so let's say you want to maximize some function of x and y, so then you have to remember the thing that we talked about last week, right? So maybe this function has these iso lines, which means that it's growing this way, and you're sure that the solution will be in that vertex. So if you want to minimize this function instead, then it's the other way around, right? So the function grows like this. So then you go here, and sorry, this line this should be parallel. So then that point would be the minimum point. But if I don't tell anything, I just say solve this problem. I don't care if you minimize or maximize. Any point in this solution space would do. So they would be good. Okay? So this is kind of a very common way of seeing optimization problems. They all work in the same way. All right? So you're going to have one more chance today to work on this in the challenge. But this time, you have to solve the question properly, not with the brute force. I want you to actually solve the question. So is there any question about this? So let me go back here. Okay, so we already solved a lot of problems that deal with modeling. The clock and strikes, driving between cities A and B, blacksmith and the ring, the spheres and the cubic boxes, chairs and tables. So before we move on, I wanted to show a video, like this is a TED video, TEDx video actually, from a researcher who actually tries to explain why the letter X is used as variable. So it's quite interesting. It's just a 2-minute video, and then you can watch later, but let's just watch it together because I think it's interesting. Makes a lot of sense for people who speak Spanish, Portuguese, and consequently, all the most Western languages.
I have the answer to a question that we've all asked. The question is, why is it that the letter X represents the unknown? Now, I know we learned that in math class, but now it's everywhere in the culture. The X Prize, the X Files, Project X, TEDx. Where'd that come from? About 6 years ago, I decided that I would learn Arabic, which turns out to be a supremely logical language. To write a word or a phrase or a sentence in Arabic is like crafting an equation because every part is extremely precise and carries a lot of information. That's one of the reasons so much of what we've come to think of as Western science and mathematics and engineering was really worked out in the first few centuries of the Common Era by the Persians and the Arabs and the Turks. This includes the little system in Arabic called algebra, and algebra roughly translates to the system for reconciling disparate parts. Algebra finally came into English as algebra, one example among many. The Arabic texts containing this mathematical wisdom finally made their way to Europe, which is to say Spain, in the 11th and 12th century. And when they arrived, there was tremendous interest in translating this wisdom into a European language. But there were problems. One problem is there are some sounds in Arabic that just don't make it through a European voice box without lots of practice. Trust me on that one. Also, those very sounds tend not to be represented by the characters that are available in European languages. Here's one of the culprits. This is the letter sheen, and it makes the sound we think of as sh. Sh. It's also the very first letter of the word shay'un, which means something, just like the English word something, some undefined, unknown thing. Now in Arabic, we can make this definite by adding the definite article al, so this is al-shay'un, the unknown thing. And this is a word that appears throughout early mathematics, such as this 10th century derivation of proofs. The problem for the medieval Spanish scholars who were tasked with translating this material is that the letter shin and the word shayun can't be rendered into Spanish because Spanish doesn't have that sh, that sh sound. So by convention, they created a rule in which they borrowed the ck sound, the k sound, from the classical Greek in the form of the letter chi. Later, when this material was translated into a common European language, which is to say Latin, they simply replaced the Greek chi with the Latin x. And once that happened, once this material was in Latin, it formed the basis for mathematics textbooks for almost 600 years. But now we have the answer to our question. Why is it that x is the unknown? X is the unknown because you can't say sh in Spanish. And I thought that was worth sharing.
I'm not sure if that's straight.
I don't think I'd be here if I didn't have it. Someone takes me shopping. Well, I don't want to think about a nursing home. I'm happy the way I am in my own
Broke my computer.
home.
All right. So, and again, you know, this is an interesting theory. I'm not sure if that's correct, but I think it's interesting to know why we call x the unknown, right? And x becomes like variables everywhere, x, y, z, and so on. There's good evidence for that anyway. You know, my computer is broken, so it's just... All right. Okay, so let's move on with money and percentage. And you know, you're going to see lots and lots of questions about this, so it's good to get practice on this. This one is pretty easy, and you should solve this even by, you know, you don't even need to write anything. This should be straightforward. So John inherited from his uncle 25% more money than his sister Jane. He wants to give her part of his money so both of them get the same inheritance. So what percentage of his money should John give to Jane? Yes? 10%. 10%, perfect. How do you get this?
12.5 over 125.
Exactly. So if John gets 25% more than Jane, he gets, so if Jane inherited X, John will inherit 1.25. He should give her 125, so both of them will share the same inheritance of 1.125. And of course, 0.125 is going to be 10% of 1.25, so John should give Jane 10%. You know, this working with percentages, okay, so here are two things, right, so that I want to tell. You know, working with percentages is tricky. Working with modular arithmetic is tricky. You know, any questions that you see with calendars, with clocks, which they have to involve modular arithmetic, right? So the numbers will grow to a certain point and then they come back to the initial value. These are tricky questions, okay? So you have to think about, I will give some questions on this later on, but just when you see questions like this, just be careful with your intuition, try to work so you don't, you know, make sure you don't miss anything. Okay, so let's go for the challenge for today. And again, the challenge will be about an optimization problem. And I want you to actually try to solve this problem in the same way as we discussed. So no brute force, okay? So be very smart about solving this problem. All right. Actually, so this question was an assignment last year, so it may take a while for you to solve it. Okay, so you would like to try the newest diet, which consists of apples and bananas. Please use the information below in order to decide how many bananas and apples you will buy and eat per day. One apple costs $1, has 50 calories. and weighs 150 grams. One banana costs 50 cents, has 100 calories, and weighs 100 grams. You would like to consume at least 2 apples and 5 bananas per day. The maximum amount of money you can spend is $50 per day, and you can carry at most 4 kilos of apples and bananas in your grocery bag. Assume you do the groceries once a day, so you just go once to do the groceries. Finally, you cannot buy or eat partial apples or bananas. The question is, how many apples and bananas should you buy and eat per day to maximize your daily calorie intake? To graph, yes, definitely. I mean, you can use graphs if you want. How do you get it?
Isn't 4 kilograms are the amount of total of apples and bananas, but not each for independent?
Yes, the total. Yeah. How do you get it?
I have 4, and this has no limit to the.
Yes.
So only 3. Yes.
Yes.
Yeah, and expand this is the biggest.
Yes. Do you want to explain, please? I can help you. Come. Okay, so you're competing too. So let me go over you guys. Okay.
Is that correct? X equals 37.
Yes.
37 apples.
Yes, this is correct. Okay, so you get 1%. Tell me. You can just scream. I can hear you.
5个瓶，然
个苹果举起8个三角，或者是
So basically, I just worked out how many grams there were
45个苹果
by what you had to buy.
，5个
That
三
was
角
what was left over.
Yes.
And bananas just had the most calories per gram, and they were also the cheapest per calorie. So I thought, and it fits just perfectly in. If you
Yeah.
buy through.
I mean, the reason is correct, but I want to a bit more formal. But the reason is correct.
Yeah.
Yeah. Yeah. Sorry. Huh? I want to hear your answer, yeah. But not only your answer. How do you do it? Huh? Yes, yes. But how do you get there? Do you have a more? Yeah. No, that's fine. Do you have a more formal method, like with the constraints and everything? Okay, so can you talk to me later? So you want this? All right. So what is your name?
Owen.
Owen. Yeah, so Owen has a solution for this question, which is perfect, right? So can you explain? You don't need to. Just give me
Okay, said, okay.
Okay, so that's good. Identifying the variables, so that's cool.
Yeah, we can get the 4 inconstant that
Okay, so identified 4 constraints. All right. So what is the objective function? All right, cool. So the objective function is to maximize calorie intake.
and this instructor can't limit the range, so we only find these 3 inconstant. Yeah.
Okay, so can I track? So the first constraint that he found was a bit too high in the graph. So if you try to draw it, you're gonna see it's way too high, which means that it doesn't constrain anything. Sorry, can I just show this? Okay, so what you have is the constraint of x bigger than or equal to y bigger than or equal 5. And then this constraint that he's gonna draw now is this one. The other one is way up there, which means that this other constraint actually is useless. It doesn't help you. All right. Cool. So then that's the solution space, yeah?
The whole. So we draw this.
Okay, the objective function.
Remove it. We can find.
So, all right. So for the objective function, so let's say y equals 0, x equals 1. Then t is going to be equal to 50. Y equals 1, x equals 0. So t will be equal to 100. So that means the objective function will move somehow like this. So if this is 2, this is going to be 4. It's going to be like parallel lines moving in that direction. So it grows in that direction. Okay, and then the last step to find the solution.
Yeah.
this is red. Come on, help me out. He's having a...
Yeah.
Yes, go ahead. So if y equals 1, then it's 100.
This is yeah. This
Sorry,
is
yeah, right. So it's the other way around.
this is 2 and this is 4.
Yeah. Sorry. It's
Correct,
the other
yeah.
way around.
So,
But it doesn't change.
So
Oh, no, it does change the solution. Right.
this is
Sorry.
solution. So x
Thanks.
equal 2 and y equal.
Okay. Sorry. Thank you very much. Okay. Let's give him a hand. All right. So I almost screwed up the answer. So actually, the objective function goes like this. So you have these parallel lines. The points that you have to verify are these 3 here. And once you draw this graph, you actually don't need to verify anything. You know that the maximum point will be this vertex here. All right, so that's probably the last question we're going to do together in this type of optimization problem. So do you have any questions on this? Okay. All right. It's very important to try to model things in your life, right? So, one thing about this class is that you shouldn't bring the lessons that you got here and then completely forget once you leave the classroom. So you have to try to model things. So, for example, let's give this example of the importance of models in our lives. So there's this perception that car accidents are relatively minor problems of local travel, whereas being killed by terrorists is a major risk when you go overseas. So simple model of the statistics from 2014, there were 32,000 people killed in car accidents and 49 killed by terrorists. And a simple probabilistic model will put these perceptions in perspective. This is from the US, but it doesn't change too much when you go to Australia, right? So except that, the numbers are kind of 10 times smaller, but, the proportions are essentially the same. In the States, this is your chance of being killed by a shark attack. So how do you compute this? Try to imagine how do you compute these statistics. 1 in 300 million. What does that mean? One person die per year out of 300 million people, right? So if you're in a population of 300 million people, the chances of dying by a shark attack is 1. I mean, it's harder than winning the lottery. Plane crash, 1 in 11 million. So if you keep moving, then you're going to see things in perspective, right? So being killed by a terrorist, 1 in 1.6 million. 1 in 1 million to be in a plane crash. So, even when you are in a plane crash, the chances of being killed is just 1 in 10. Bicycle crash. Now, things become a lot more scary, right? 75,000. Choked to death, 68,000. That gives you a perspective, right? So when you start looking at these statistics, then you realize where things are. 1 in 2,000 die by drowning. 1 in 5,000 car accident. 1 in 28 stroke. 1 in 7 cancer. 1 in 6 heart disease. Now, you shouldn't be worried when you go to an airplane, but you should be very, very worried when you eat a pizza and try a cheeseburger. Yes.
So it's not per year; it's like one person. Like it's that person's population.
Yeah. It's the chance of that person dying from that cause. Yes. Yeah. I mean, there are the statistics per year, but.
1 in 6 people in America die of heart disease every year. That sounds like what would be done.
You can't imagine? Okay, looking at this room, you pretty much, like 1/3 of us will die of some sort of cardiovascular problem. 1/3 will die from cancer. That's the statistics. So, There's nothing that, tells against this. It's very rare you're going to die from any out of these other problems. But the point is not this. The point is to kind of understand things, right? So when you model things, things become a lot clearer, and then you can make more informed decisions about your life. That's not only about how you're going to die, but how you're going to live. The decisions you make financially and in your personal life too. Okay, so I have time for one last example. Yes. Okay, so simple models may protect us from a tendency to underestimate the frequency of coincidences. How many of you have a family member who had a clear dream one night that a serious car accident would happen just hours before a friend or relative's Holden Commodore hit a tree? So we always hear this kind of stories, right? So there's always these things about someone predicting the future somehow. I'm going to show you that this is just the statistics. That's going to happen. So let's try to build a model, very simple one. There's not zero probability of anything to happen. So there's a probability that someone will have a dream that will come true. So assume the probability that a particular dream will match an event in real life to be 1 in 10,000. But it could be 1 in 100,000, 1 in 1 million. It doesn't really matter. Just give a very, very small probability. So this means that such occurrence is quite unlikely. The chances of a non-predicted dream is going to be 9,999. Then you assume that the sequence of dreams are independent. So you have to make this assumption, otherwise the solution becomes complicated. So that's the thing we're talking about modeling, right? So you have to make it simple enough, but realistic. And let's assume that it's realistic that dreams are independent. So then what is the percentage of people who dream every night that will have a predictive dream during 1 year? So the probability of having a non-predictive dream is going to be 0.9999. Probability of having 2 non-predictive dreams is going to be 0.999 squared, 3.999 cubed. Because this number is smaller than 1, and what happens when I multiply it together many, many, many times? You go to 0, right? So it will be very, very small. So let's say n. So let's say n is equal to 365. So that means in 1 year, the probability of having non-predictive dreams is going to be 0.999 to the 365, which means 96.4. Now, so let's say 96.4 of people will dream every night and will have a non-predictive dream. That means that 100 minus 96.4 will have some predictive dream. And that happens all the time. You cannot underestimate these probabilities because even, very unlikely things can happen. And over time and giving it many, many chances, it will happen. So that's the goal of this question. Okay, so yes?
But that doesn't actually factor in the chance of a car crash happening in the same night as well. That's just the chance that they'll have a dream that roughly relates to.
Yes, but assume that a car accident will happen anyway. Yeah. It's just a predictive. And if you make these two predictions, then the probability will be smaller, but it cannot be 0. Okay, so that's it for today. Thank you very much. So can I get your ID? Your ID? So well done.